The second lab session is dedicated to analog modulations, in particular to the amplitude modulations, and we will start with a double sideband modulation. In particular, in this case, the modulating signal is a very simple signal, a sinusoidal with a frequency of 5 kHz. And basically, in this first exercise, we will plot the modulated signal, its power spectral density, we will analyze the effect of a non-coherent receiver, and we will plot the performance, the signal-to-noise ratio for a coherent receiver. In the double sideband modulation, the modulated signal is the product between the carrier, here in red, a carrier with frequency 50 kHz, and the modulating signal, in this case the sinusoidal signal, and the product is here in blue, a very simple shape. The power spectral density, this axis is in kilohertz, not in hertz, sorry, is the typical spectrum for a double sideband modulation. The carrier frequency is 50 kHz, and we have the spectrum of the modulating signal, two deltas at -5 and +5 kHz, centered now at the carrier frequency. Carrier frequency is 50, and the deltas are in 55 and 45 respectively. If a non-coherent receiver is used, when the phase shift is different than 0, increases here, this axis is scaled by a pi factor. Here we have the increasing of the phase difference up to pi, and here up to -pi. It's evident that if we don't have a 0 difference, we don't have a coherent receiver, the signal-to-noise ratio is going to be lower and lower. And in any case, the signal-to-noise ratio is higher if we previously filter the signal to limit as much as possible the noise power, obviously. And then here we have the plot of the signal-to-noise ratio as a function of the noise standard deviation, and of course with a previous filtering to reduce the power of the noise, the signal-to-noise ratio is higher for every value of the standard deviation. In the second section, we repeat this procedure for the single sideband modulation. In this case, we have a lower sideband variant. This means that the component that we had previously at 55 kHz is removed, and we only have the component at 45 kHz. Again, the non-coherent receiver is going to degrade the performance when the phase difference is different than 0, a non-coherent receiver increasing from 0 to pi or from 0 to -pi, the signal-to-noise ratio is decreasing. Of course, to filter before of the demodulation to limit the noise power will help to increase the signal-to-noise ratio. And as a function of the standard deviation, the signal-to-noise ratio is always higher with the previous filtering than without this filtering. Using a demodulator for an amplitude modulation instead of the demodulator for the single sideband modulation, the result is going to be the same one because the receiver is the same one, a coherent receiver. This can be seen in these two pictures, where basically with the two receivers of the toolbox, of the MATLAB toolbox, for the demodulator of an amplitude modulation or a single sideband, the performance is the same one. The receiver is the same one, it's a coherent receiver. Finally, in the third exercise, we have a conventional amplitude modulation, which basically is a double sideband with a carrier. The only difference with respect to the double sideband is that now we'll need to add the carrier to the output of the double sideband modulator. Now, with the addition of the carrier, we have the shape of the modulating signal in the envelope of the modulated signal, in this case a sinusoidal function, In the spectrum, we have the component of the frequency response of the carrier, a delta at the carrier frequency, and then the shift to replica of the spectrum of the sinusoidal with deltas at plus and minus 5 kilohertz with respect to the carrier frequency. Again, a non-coherent receiver will degrade the performance, and filtering is improving the signal to noise ratio for a given standard deviation of the noise.